Let's now solve the Ramsey-Cass-Koopmans model in Mathematica using the relaxation method. First, I would like to draw your attention to this link here. It's done by the original authors. Parts of my code are taken from their supplied solution, so all credits to them. Also, it's definitely worth checking out. I simplified the code a bit, not to make it overwhelming at first. If you're not too familiar with Mathematica, I think the syntax can be a bit much. But if you want to have the full depth and all the sanity checks, check out the website. They also have different macro models, solved also by MATLAB if you prefer this over Mathematica. So it's definitely a resource to consult to if you plan on employing your relaxation method for your model. So what we start with here is first setting the model parameters, the model settings here. And I try to keep the notation consistent. If you're not too familiar with the Ramsey-Cass-Koopmans model in this channel, there are a couple of good videos explaining it in detail, how to solve it, how to arrive at specific results. I assume you already watched those. If you're a bit shaky in your understanding of the Ramsey-Cass-Koopmans model, I highly recommend checking them out. But if you are, if you already watched them, you will see that all my parameters are named exactly like they are named in the theoretical videos. Also here, I really want to, if you ever do this yourself, I can recommend Mathematica to the extent that everything that has to do with mathematics is so nicely displayed. The syntax is very compelling. Problem is if you start having to deal with large matrices, the syntax becomes a bit messy. So there's a cost to everything, I suppose. Anyways, so first you set your parameters of the model here. You can set them according to the theoretical limitations. And here I set my inverse elasticity of intertemporal substitution such that, as Barrow and Salah-Martin suggested, that we have a constant Saverings rate. This in itself is not necessary, but it helps to compare the results. So these are setting the parameters. Given the parameters, we can set up our ordinary differential equations, one for how capital changes and one for how consumption changes. These are exactly supplied by the videos, by the theoretical videos you might have watched already. Note here that we implicitly use a Cope-Douglas production function. This is this part here, so we don't do it for the regular the general production function. Here again we have this n1, n2, and 3 from the theory slides before, which are exactly the number of initial conditions, the number of endpoint conditions, and the number of static conditions. Here in the Ramsey-Cass-Koopmans model, we don't have any static conditions. We need to have our initial condition. This is our starting point. In principle, you would only need a value for capital here, since you would, given the capital, the consumers then optimize their consumption, and this is already implicitly selected by the model. So you have some initial condition and you have the endpoint condition, which we can solve for, again exactly as you saw it in the videos. So your K star and C star are then put all together in one vector as the endpoint condition. Here we set up the number of grid points we want. So this is M, capital M. Sometimes with Mathematica, I think it's a bit tricky to deal with capital numbers, capital letters, because Mathematica doesn't allow you. So often letters are blocked. Also T later on will be blocked, where we had the vector of all the time periods. So here I cannot call it M, I can only call it the number of grid points. Here we selected 100. In principle, you can increase this number at cost of computation time. Then you want to find some function, how you want to evaluate the loss. Should your mean loss be smaller than some convergence threshold epsilon here, or should the maximum value, for instance, be smaller than a given threshold? This is your choice. You can set up some maximum number of iterations, not to be stuck in an endless loop. If you misspecify, maybe you might end up there. And to break the loop, here we have set a number of maximum iterations of 20. And this one is a bit of a computational condition in order to assure only only positive values are included in the Jacobi matrix. You have, like, whenever something is 0 or negative, maybe can happen due to some rounding errors, they will be automatically put to a very small yet positive number to assure invertibility of your Jacobian matrix. Finally, we set the initial guess. So the initial guess of the convergence behavior, you have an initial guess, we have the endpoint condition, we have the starting condition, the endpoint condition, and the initial guess is what we think is the optimal transition. This is just some solution for every time point. In our case, I set it up as a linear transition path. You will see later what I mean by that. Here we set up the time mapping. We said, okay, we have this infinite time horizon, and in order to deal with that, we map it into this interval of 0, 1, and to map it then back, we need the inverse of the function we had on the slides. Let's briefly explore this function a bit. So what it does here is it takes the original mapping from infinity, so 0 infinity to 0 1 is this function here, and the larger your nu is, the more compression you get of the late past into a small section. So here the immediate past, everything between 0 and 1, let's say, is almost taking up the entire span, and everything after 1, let's say the interval between 1 and 10 is all compressed into basically the very last end of our unit interval. So the information is much more compressed, so the time is much more compressed in the late past than in the early immediate past. And if you play with your nu, you can vary this. So now it's much lower, and here you see basically the interval from 0 to 1 now does not take up basically everything, but only about half. And the other half now is then taken by everything after 1. So with your nu, you can vary how your time is compressed so your time from 0 to infinity is compressed into the interval 0, 1. Now if you look at this time function is exactly the inverse of the time function we had in the slides, or also here, for the simple reason that we start off with this unit interval and then just need to translate it back into this 0 infinity range. Okay, so we have this defined, and here also just, I mean, you have all the comments here anyways, but for clarity, delta tau here is, you know, the width of the time points, and here you have the tau list, which is basically the capital T from before. So yeah, this section specifies everything time related, and here you have the mapping back to from 0 to 1 to 0 infinity, which is of course, so this one is just to monitor the warning messages. So long story short, here we come up with the mapping from 0 to 1 to 0 infinity. Now the computational part of the algorithm. So first we need to compute the error we imply with our initial guess. So because if you remember the initial guess, we said there's this linear trajectory of into the steady state. But of course this will be wrong. So what's the error we imply with our initial guess initially? First, some notation. Here we have nt, small nt. This is what you find in the paper to be denoted as capital N. In Mathematica, starting variables with capital letters is typically reserved for functions, which is why I can't use nt here. And 1, again, number of initial conditions, number of end conditions, and n3 is the number of stationary conditions, which is 0 in this application. But sometimes I like to keep the formulas intact if it doesn't cause too much confusion, for you to see the mapping from the theory of the slides or the appendix to the code. Good, so nt is the total number of constraints we have. Then we say, okay, our first solution is our initial guess, and then we start calculating errors. And if you remember at slide 7, we saw that for the starting point and the end point, different conditions apply. So for the grid points in between, it's quite the same, but for the first point and the last point in our discrete time grid, different rules apply. And this is why we calculate it kind of separately. Here, as the starting point, as the end point, the starting point is quite simple. So this one just says pick the first element of our initial guess, because it's a vector, right? The vector starts at the first point and then goes to the last point. The last one is the latest, the first one is the first. So the first element here is our initial guess at time 0, if you will, and subtracted with what the initial condition is supposed to be. So how much did we get it wrong by our initial guess? Okay, and for the endpoint, the same applies here. Don't let yourself be confused by this range argument. This range argument is a way of Mathematica to create a sequence of starting, natural numbers. You start at 1, 2, 3, all the way until, for instance, n1. This is if you supply one argument. If you supply 2 arguments here, you have, or let's say maybe here it's easier. Range first, so this is the starting value. Let's say this is 5 and this is 7 here. Then you start with 5, 6, 7, and the range of these two, is just the sequence from starting at 5 going to 7. This is what you also, for instance, in R, you could write it as, n1 to n2, for instance, or whatever. Or you from 1 to n1. In our case, n1 is 1, so So this is just 1. So this is what the range does. So the nice thing about Mathematica, when it has to do with math, it looks very slick, very simple, very comprehensive syntax. When you have to do with let's say a bit more you know, programming, it's a bit out of the ordinary. Let's say if you're used to other programming languages like MATLAB, R or Python. So yeah, this is why it might look a bit involved, but that's what I'm trying to do here, is to kind of explain that this actually just is a quite simple procedure, usually. Good, so yeah, we basically just take, okay, this sequence here are the initial guesses, right? So a solution at this point is just our initial guess here. Initial guess is our solution. So the solution, and here we pick basically the last value, because we only have one end condition. So we pick the last value of our initial guess and see, okay, how is it different from the end condition, and this is how we get the endpoint error. So far so good. The involved bit is now the in-between errors. So everything between 1 and the last one. Good, and this is what this chunk here is. This chunk here directly associates to what we see in the slides, or also the appendix of the paper, as equation A2. So this is directly, I also typed it here again for you to see it. Every element in this bit here, in this table, refers to an element in this equation. It's all wrapped, so the flatten argument is wrapped around it. What the flatten argument does is it gets rid of the tendency of Mathematica to have nested lists or nested vectors, right? You have a list inside a list, or a vector inside a vector inside a vector. And there's a lot of hidden structure, and to make it all just one nice vector without any structure in it, this is how why you use flatten. This will reoccur, so I thought I'm going to explain it. If you copy the code, you know, you can just double click, press F1, you get to the help function, then you get all the functions explained to you as well. Or you just Google it, you know. But this flatten basically just makes it a nice vector. Okay, so we said, okay, the error is at first is the error of the start point, at last the error of the end point, and in between this error function. So let's look at it. So first we evaluate our guess, right? This is the y. So we evaluate, okay, how much did the system change in our guess, in our initial guess in this case, and this is what this first table here does. It basically compares, okay, how much did it change from the, let's say, 5th grid point to the 6th grid point, and from the 10th grid point to the 11th grid point, and evaluate and compute it. And then we say, okay, how much did our initial guess change? And the second bit is, how did the system change? The second bit here, after the minus, we see, we basically see, okay, we look at our system of equations, and then the second bit here is evaluating the average arguments in between the grid points. This is what you find in the slides or in the appendix of the paper, to be denoted on slide 6. So there you have this tau bar, for instance. Tau bar is exactly this. Y bar is exactly this. And why do we have this exact kind of time structure? Well, it basically, the reason why the arguments are combined like this is basically described in equation A1 on slide 5. So this is f, so this one is in principle f times this time function, and this is exactly what we hear. So this is the system of differential equations. This is our f, and and we need the time function there kind of to make this squishification from the infinite time horizon to a time interval between 0 and 1. And since this is basically just the Mathematica way of writing the equation A2, we just calculate basically how much did we get the change of the system wrong by our initial guess. So we evaluate the system and we evaluate our initial guess. How much did we get it wrong? We put it in one big vector. We glue the starting error on top of it, and at the bottom we glue the endpoint error to it, and we end up with a normal vector with all the errors. Yes, so this is a structure that will reoccur in the loop later on, so make sure to understand it. But again, just look at the equations A1 and A2 in the paper, so in the appendix of the paper or in my slides, because that's exactly what it is. With this error function at hand now, we try to minimize this one. And since it is a nonlinear, highly dimensional system, we have to rely on the Newton-Raphson method to solve for it iteratively. And as you saw in this small introduction to the Newton-Raphson method, we need the first derivative for this. The first derivative of a vector, in case you don't know, is what's called the Jacobian matrix. The Jacobian matrix is a matrix full of partial derivatives. Yes, so this is also what you see in the equation A4 of the slide. So in the appendix, or on the slide 8 of my slides. And here we can basically distinguish into two key components. The derivative of the error function with respect to the lower grid point or the derivative with respect to the function evaluated at the upper grid point. And if you don't know what this means, maybe have a look at the slides again. But this is how you can nicely and simply compute the Jacobian of this highly dimensional system. Because usually also just calculating Jacobian can be quite involved, and later we need the inverse of Jacobian, right? So, and this is in itself quite involved. So if you have a nice way to break it down, that really makes it computationally much more feasible to apply this method. Finally, we have to calculate, or we don't have to, but it's smart to calculate the endpoint Jacobian value outside of the loop, because it's constant and would only add to unnecessary computational burden. And to make the method applicable to very complex tasks, this is to be considered. So here in this JAC endpoint variable, we store the Jacobian value of the endpoint. Okay, and this is when now the incremental improvement starts. So this is where we start looping over solution after solution after solution, like you saw in the Newton-Raphson introduction, to iteratively improve our solution. So first, with these algorithms, you need to first initialize them. So first we have to have some loss function, basically some criterion which we measure. So if our relative error in this case will be sufficiently small, we say we stop. So this is good enough, basically. But we have to initialize this somehow, and we have the relative error list, which basically just saves all the relative errors to see to keep track of the improvement. Iteration counter, so you always need some exit criterion. So if, for instance, your algorithm doesn't converge or doesn't converge quickly, you want to say, okay, at least try this many iterations in order to before you stop, basically. And this iteration counter counts all the iterations so that we know how quickly does it converge. Solution storage is for later, to store all the different solutions, to see kind of how this is only for pedagogical reasons why I have this in there, to see kind of this iterative improvement you have later on, but in the end you're not interested in the in-between solutions, but you only want the last final solution. And yeah, this is basically just to we say, okay, our initial guess is the first element of our solution storage. So in the solution storage, we start with the first vector being our initial guess, and the other ones will be filled up as we go. Okay, and the loop starts here. So as long as the relative error is larger than what we decided the convergence, the minimum, so we decided this convergence epsilon beforehand, and we said, okay, this is how small we want our relative error to be at most in order for us to consider it good enough. And the smaller we make this, the more restrictive we are. So if, as long as the relative error is larger than this epsilon, we keep going, we keep iterating, we keep improving. Or of course, we say if the iteration count is smaller than the maximum iteration count, we also keep going. So as soon as one of those two criteria are violated, we exit the while loop. So while we're too far off and we're still not exceeded the iteration limit, we keep going. This is what the statement says. And then we have to deal with some Mathematica trickery. So first we evaluate the initial condition and so where it goes in the matrix. Here it goes in position 1, 1, and this value is also 1. So here in blue commented out, I have the bit more complex kind of general results, but I figured it's nicer to have it kind of boiled down, because in the end this step is cumbersome enough to not let ourselves get confused by confusing notation. So first we find, so this position vector basically stores all the so where the elements go, right? Where the elements in the in this Jacobian matrix go. This is what we saw in slide 8, right? We have this sparse matrix with all these S's in it. So we have this S0, S1, left side, right side, etc. This equation A4 in the paper, there you see this big matrix, and basically these position vectors just tell you where in our matrix it is positioned. This part that we're dealing with now. So the initial conditions is of course positioned at matrix element 1, 1, and we have the value of 1 because this is the initial conditions that we the derivative of the initial condition. Okay, and then the body of the rest is calculating the position of the left Jacobian blocks and getting the values of the left Jacobian blocks. And then we need to calculate the position of the right Jacobian blocks and calculate the values of the right Jacobian blocks. So in the end, we end up with a Jac position vector and a Jac value vector. So that's Jacobian position, the position of my individual block matrices and the values of my individual block matrices, all put together. Yes, all put together. And what we do here is partly just keeping count, right? This is what the position does. It keeps count. It kind of has this, sequence that increases depending on how large your blocks are. So this is again just unnecessarily complicated for our simple case, but I think it's still key to see that it very neatly generalizes. But if you ever had to do with loops and a lot of indices growing and changing, you know, this is not alien to you. So basically it just says, okay, where does the new block go? And then of course we have this Jacobian left and Jacobian right. Where is it? Jacobian right down there, where we basically just evaluate the Jacobian matrix at our average tau value, so in between time point. And this is a lot of code for a very simple task, which is to save all the individual positions of the block matrices in the Jac position element and evaluate all the Jacobian values, all the Jacobian matrices we calculated in the general case up there, evaluate them and store the values in the Jac value vector. So with all this at hand, we can now calculate the Jacobian matrix as it is. So we take the values here, so the values, so this one, we take the values and we take the positions and we basically create this sparse area or sparse matrix in this case with the location information, the position information and the value information that we previously just calculated. So this thing Jac here is the Jacobian matrix as a matrix. Before it was two separate things, now we glue it together, and with this we can now calculate our solution for the linearized system. So here I have it. So solve the linearized system. Remember, we turned a non-linear system into a linear system, or we approximate it now with a linear system rather, and now we try to see, okay, where does it equal to 0? Where is the so-called solution? And this is exactly what we also saw in the slides on, where was it? On slide 7. So this is exactly the final step, where we calculate, okay, so how do we need to improve, right? So what is this delta y, this change in delta y? How much do we need to move from our current guess to get to our approximated solution? Okay, and since we have this equation here, what we do is we put this error function of our current guess on the other side, so we end up with this minus error, so this negative error function, and then we need to divide by this this Jacobian divide, you know, take the inverse of this Jacobian. And how to do this in Mathematica, this is linear solve. So basically, whenever you have a system that's like ax equals b, and x and b are vectors and a is a matrix, you need to supply the first argument is the A and the second argument is the B. In a general case, and it automatically solves for the x, so you don't need to supply the x as an argument, and this is, so we get this x as delta y here, so we get this missing, so how much do we need to move in order to get to our approximated solution. And with this now we can update our solution. We say, okay, the solution we have now, or we had previously, that was in the first run, this is our initial guess. In the second run, you know, this is more and more refined. We have this current solution, we update it, we get a new solution. The next line here is just for computational stability. This is not part of the algorithm as you know it from the slides. It just might be because keep in mind, we work with not the exact solution, but we work with an approximate solution, right? And just by mere coincidence, it might happen that one of our suggested solutions, if we're, let's say, far off of the true one, and we just give it a try, we linearize the system, we find the solution, and we might end up with negative capital or negative consumption. And that doesn't make any sense. So this next line here is just to assure that we only have positive capital and positive consumption. So we say, okay, if it's negative, if it's too small, we say we want to set it equal to some minimum solution value, which is a very small positive value in our case. And then we just glue it onto the solution storage vector, which basically just to be used for illustration later, to see how, you know, how the algorithm improves the solution like iteration by iteration. Okay, with this new solution at hand, we can now calculate the new error, right? Because the solution, after all, again, is an improved but still approximate solution. So we calculate how wrong did we get it, and this bit here is the calculation of the new error vector. And the new error vector is calculated exactly the same way as you saw it before for the initial guess. So we evaluate our system, we evaluate the system, the true system. When I say our system, I mean our approximated system. Then we evaluate the true system. We see where did we get it wrong, and then yeah, end up with a new error vector. And the last bit here is just to calculate the convergence criteria. So the relative error is basically the mean absolute error of each grid point, of each time point, and the mean is just a choice. You could also say we look at the maximum error. We want the largest deviation from the truth to be at most as large as this. Yeah. But here we say, okay, the mean error, and we can say the mean error is some number, right? This is just some number, and we're gonna use it as a convergence criterion, right? Because up there for the while loop, we say as long as this number, which we just calculated, the mean absolute error, is larger than some convergence epsilon, which is a very small number, we keep on going, right? We keep iterating, and if we're small enough, we stop, and we get to pick what is small enough. And finally, okay, this is just for storage, so we keep track of how fast do we converge, and finally we increase the iteration counter by 1, because in the end we might just time out on iterations, and then we would also stop, or we would want to know how many iterations does it take for us to converge. We'll see it later in the output. Okay, and this is the end of the loop. So once the error is small enough, we exit the loop and we say, okay, our final solution is the last solution which we found, and then we're going to glue the time list to it. So we will later see that we have kind of a reference to basically for visualization again, so that we see, okay, each grid point is associated with some time period, and to make this nice and visible, we just glue this there onto the final solution vector. And also we create this iteration log matrix, which basically says, okay, we're gonna keep track of all the relative errors that we calculated. It's basically the same as this relative error list, only a bit neater to look at, and then we're done. Right? So basically the solution, the last solution we calculate in this update step. If this produces an error that is small enough, we exit, and then this is basically just cosmetics.